Welcome to A-Level and AP Physics. In today's lesson, we will discuss past paper questions from March 2024, Paper 4, Variant 2. As always we will discuss these questions in detail so you can improve your conceptual understanding of physics and also you can have better understanding of these exam questions. In order to get maximum benefit from these videos, always try questions first of all by yourself. It doesn't matter whether your answer is correct or incorrect. What matters is whether you have tried or not. When you try to answer a question, it helps you to understand your misconceptions and also it helps you to realize your weakness. And that is what is most needed for understanding of physics. When we figure out our misconceptions about any topic, then we can improve our understanding. So always try questions first of all by yourself, not just simply look at the mark scheme or simply look at the solution. To improve your understanding, your own efforts are very important. So always try first of all by yourself. Let's study together, let's improve together. Question 6 part A says, a small coil C has 64 turns and cross-sectional area 0.71 centimeter square. The coil is placed inside a solenoid as shown in figure 6.1. So coil C is placed here. The center of coil C is on the center axis of the solenoid. There is a constant current in the solenoid. Coil C is moved through the solenoid from position X to position Y. On figure 6.2, sketch a line to show the variation of the magnetic flux linkage in coil C with position as it moves from X to Y. Means when we move this coil C from X to Y, what is the change in the magnetic flux linkage? So first of all, we need to understand magnetic flux linkage of coil C. So magnetic flux linkage of coil C, this will be equal to the number of turns of coil C, cross-sectional area of coil C, and the value of P, magnetic flux density. As this coil is placed inside solenoid, so the value of B is constant. Magnetic flux density means the magnetic field inside solenoid is constant. So we can say inside solenoid value of B is constant. So this is the main concept you need to understand. Inside solenoid B is constant. So this is the main concept. So inside solenoid magnetic field is constant, mean magnetic flux density is constant. So it means this quantity is constant, cross-sectional area of this coil is constant, and number of turns also constant. So it means that flux is constant when we move from X to Y. So it simply means that we need to draw horizontal line. You can draw anywhere. So simply you can draw one horizontal line. If you have drawn this one, you will get 1 mark for this question. For the second part, we need to explain the shape of line in part A1. We have already discussed why we draw the horizontal line. So now you need to explain why you draw the horizontal line. We have already discussed that point, so simply I will write again. Magnetic flux linkage for coil C, that is equal to NBA. So NC is constant, BC is constant, AC is constant. So magnetic flux linkage through coil C when we move from X to Y, that is constant. So you need to write down these points. So simply you can say in this case, the first point you can say is constant flux density inside coil. Flux density simply we are talking about B. Then flux is equal to BAN, means the flux linkage. B is constant, E is constant, and N is also constant. So if you have written first point, you will get 1 mark, and for the second one, you will get the second mark. So this is how these 2 marks will be awarded. Third part says coil C is now held stationary at X. The current in the solenoid varies so that the magnetic flux density B at X varies from time t equal to 0 to time t is equal to 40, as shown in figure 6.3. Calculate the magnetic flux. Calculate the maximum magnetic flux linkage in coil C. Maximum magnetic flux linkage. We have already discussed that magnetic flux linkage through coil C, that is equal to number of turns of coil C, cross-sectional area of coil C, and value of B, magnetic flux density. So in this case, N is constant, AC is constant. So when this value will be maximum, so this value will be maximum when B is maximum. So when B is maximum, so if you look at this given graph, here B is maximum. So this is maximum value of B. Now simply we need to plug in values. So we have N number of turns of coil C, 64. Cross-sectional area was given to us, that was 0.71 centimeter square. So we need to understand 1 centimeter, this is equal to 10 to minus 2 meter. So we have square, so we have to square these both sides. So we can say in this case 1 centimeter square will be equal to 10 to minus 4 meter square. So we have to multiply this one with 10 to minus 4. And B is maximum, and its value is equal to 0.080. Now if we solve this one, we will get 3.6 times 10 to minus 4 Weber. We will get, this is the answer, Weber. So simply you can write down up to SF, because our given data has 2 SF, so the final answer also should have 2 SF. So we can say 3.6 times 10 to minus 4. Unit is already written here. So if you have got the right answer, you will get 2 marks for this question. And if your answer is wrong, for example, you got this wrong answer, but you have written formula and you have written these values, still you will get 1 C mark. Part 4 says on figure 6.4, sketch a line. Sketch a line. It doesn't mean that you need to sketch a line. It means you need to sketch a graph. So don't get confused with this sentence, means with this language. Sketch a line means sketch a graph. Sketch a graph. It can be a curve, it can be a straight line. To show the induced electromotive force E in coil C from time t equal to 0 to t is equal to 4t. So simply we need to sketch a graph between induced EMF in coil C against time. So first of all, let's try to understand induced EMF. This is equal to negative of d phi by dt. So now simply we can say we have D, and magnetic flux linkage, this is NBA. So this is NBA divided by dt. So in this case, N is constant, A is constant. So simply we can take these two quantities out. So we can say this is negative, we have N, and here we have A. And here we have dB by dt. dB by dt. So we can also simplify. We can replace these two quantities with one constant. So we can say, let's say this is K is a constant. So here we have dB by dt. And dB by dt, if you look at this graph, B against T, dB by dt is simply, this one is the gradient of BT graph. So this is gradient of BT graph. That's all. So we need to look at the gradient of this. Here gradient is equal to 0. It means until t is equal to 0, means from here to here t is equal to 0. So it means this value is equal to 0, because gradient 0, it means EMF is equal to 0. And now if you look at the second part here, this gradient is positive, but here we have this negative sign, this minus sign. It means that negative, so it means EMF, this one is positive, so the EMF has to be negative. So we can draw here, we don't have the exact value, so simply you can draw here because the scale is not given to us. So simply we can draw the line here. Now we need to compare the gradient. From here to here, you can see along time axis we have two small squares. Along b axis we also have two small squares. Now if you look at the gradient of this one, in this case we have 1 2 3 4, means 4 small square along time axis, and also we have 1 2 3 and 4, and also 4 small square along b axis. So it means gradient of this part and this part is the same, but this gradient is negative, so EMF has to be positive. After time 2t, EMF has to be positive, so it has to be positive from here to 4t, so 4t. So this is very important. So these two gradient, these two values, means the value of induced EMF here and value of induced EMF here has to be the same, because gradient is same and we have constant here, this constant is also same, so it means EMF is the same, but the sign polarity has to be opposite. If you draw this one positive, you can draw, that is also acceptable, then this one has to be negative. If you have drawn this one negative, this one has to be positive, but magnitude should be the same. So this is how simply you can draw. Part B says a metal spring rests on a smooth table. The turns of the spring are equally spaced. The ends of the spring are connected to a DC power supply as shown in figure 6.5. The spring is connected to the DC power supply using flexible leads. The spring is not under tension. With reference to magnetic field, describe and explain the change in the distance between the turns of the spring when the power supply is first switched on. So first of all, simply we can imagine power supply is connected here, so we can say this side is positive and this side is negative. So in this case, current will flow like this. So here direction of current is up, here direction of current will be down, and here direction of current will be up, here direction of current will be down, and so on. So one thing you can see from here, current in each coil flow in the same direction. So if I simply draw one turn here and if I draw another turn here, you can see current here is up, current here is down, current here is up, current here is down. So current in same direction, so we can say same direction of current in each coil. In each turn, you can say, or simply you can say in each coil. Now you need to understand, if we have two wires, very basic concept, if we have two wires, current flow in the same direction, so these two wires, they will attract each other. So they will attract each other. So simply we can say they will attract. But if current flow in the opposite direction, so means current in one wire is up and in other wire current is down, they will repel each other. So this is very basic concept. Even we have studied this one at IGCSE level. We can also use Fleming left-hand rule and we can prove this one. But for simple understanding, you need to understand wires they will attract and when they will repel. And same is true for the coils. Current is up, then is down. So simply you can say current is up, then is down. So direction of magnetic field. Let's say here I'm just drawing one here. Let's say this pole is N, this pole is S. So the pole here, this is just for reference. So this pole has to be N, this pole has to be S. So current flow like this. So I'm saying if the coil is placed like this, so this is coil. So this side will be N, that side will be S. So from my side, so coil is a loop like this. So I'm saying coil is like this. So you can simply see. So this is here. So current here is up and this side is down. So thumb is pointing to the left. So it means left side will be north pole. So this pole is S, this is N, so they will attract. So it means these two coils, they will attract each other. So that's the main point you need to understand. So this is the basic concept. This is basic concept. So this is what you need to understand. So these two turns means each turn they will attract each other. So they will get closer and the distance between turns will decrease. And this question is a common question in past papers, and this is kind of tricky question. So you need to master this one. What is happening here? If this is clear to you, maybe in your coming exam you will see question about this concept. So try to master this one. If you have any questions, you can leave your questions in comments and I will try to answer as soon as possible. And if you are looking for extra resources, you can also join Patreon. On Patreon, you will find more resources. Now let me show you how you can write down the answer. To answer this question has 3 marks. So you can write about these points. First thing you can say, current in spring creates a magnetic field around the spring. As we have discussed here, current in the coil, current in each turn, it produces its own induced magnetic field. Magnetic fields around adjacent turns interact to cause an attractive force to be exerted between the turns. So we can say cause an attractive force to be exerted between the turns means they attract each other, simply you can say, and distance between turns decreases. Question was asking you to describe and explain. So in this case you can say distance will decrease because current will cause induced magnetic field in each turn, and magnetic fields of two adjacent turns, they will attract each other, so there will be attractive force. Mean due to interaction between magnetic field there will be attractive force and the distance between turns will decrease. So very simple concept. So you can say in current, so you can also write down like this: current produces induced magnetic field, or simply you can say induced magnetic field in each turn, or you can say simply induced magnetic field. So I'm just writing in detail, and that cause attractive force between turns and distance decreases. So this is the main concept. So distance decreases. So this is what you need to understand. I hope it makes sense. That's all for today's video, and remaining questions I'll be uploading as soon as possible. If these videos are helping you, please like and subscribe, and also share with your friends. If you like and subscribe, that is kind of encouragement for your teacher. See you in next video.